the first thing I'm going to do is I'm going to draw a free body diagram. And I'm going to draw it for my, the cylinder or whatever the pulley that the rope is wrapped around. And then I'll draw a second one for the bucket, right? And so the pulley or the cylinder has got, force tension down, kind of like we were just talking about. It's got, its own force gravity. I'm sure we can, it's got some mass, so it's got its own force gravity, and it's got, some supporting force support up, right? And the hanging mass has got force gravity down and force tension up. Now, one thing I want to point out to you guys here is that these two force tensions are equal to each other, because there's no, as we just spent a good amount of time discussing, there's no mass in between those two tensions, right? Even if we look at the picture here, I can zoom in, we can see that there is no mass in between there. So that means the tension in the rope in that space is the same or constant, okay? So we've got our free body diagrams. Are there any questions on the free body diagrams? If I want to be really accurate, I should make sure, and I think it actually did turn out that way, that this force gravity is larger than that force tension, and these two arrows should be the same length. I didn't really get the same length thing, but I think you can kind of see this as bigger than that because it's accelerating downwards. Now, the next thing to notice is that what we're going to do is we're going to write out our kind of like equations, our net torque and net force equations for each thing. So we'll write net torque equals I alpha for the pulley, and we'll write net force equals MA for the hanging mass. Now, notice that since both the support force and force gravity are acting at the axis of rotation, there's no torque there because they're a radius of 0 from the axis of rotation. So the only thing that's applying a torque is force tension. So what that means is we've got force tension times radius equals I alpha. Now, before I go and elaborate on this, we need to think about pluses and minuses, right? And one of the things that we got to think about is bending the axis of acceleration, right? And so what we're saying here is that clockwise is the positive direction, right? So that means force tension is producing a clockwise torque. So that's going to be a positive torque. And we've kind of done that, this positive there. But the important thing is that force gravity is positive and force tension is negative, right? Because we bent our axis of rotation so that clockwise is positive and down is positive. So when I plug in my net force symbols, I'd say plus force gravity minus force tension equals MA, okay? Again, I don't want to rush through this because it's a little tricky. Are there any questions? Okay, so I'm just going to use a capital R so it's really easy to see that. So the big thing that I want us to focus on is how many knowns and how many unknowns do we have? And one thing to know is that if you have one equation, you can only have one unknown. But if you have two equations, you can have two unknowns and you can do some substitution. And that's going to be our end game here. That's what going to be our goal. We are going to do a substitution from one to the other, okay? So we'll get there in a moment. The first thing we're going to do is get some simplification. We're going to do some simplifying. So let me scooch this over here. Let me scooch this over here so we have a little more space to work with. So we're told that this is a like a cylinder, and the cylinder has got a rotational inertial equation of 1/2 mr squared. So I'm going to say, okay, so force tension times radius equals 1/2 mr squared times alpha. Okay. Now let's do a little check-in on what values we have. If we look up at the top, we've got the mass of the bucket, we've got the radius or diameter, and we've got the mass of the pulley. So those are the three values we have. So let's take a look down here. So in our two equations, force tension is a question mark, radius we've got, mass we've got, radius we've got, alpha is a question mark. Force gravity is just mg, right? So it's just mg. So we can say we've got that. Force tension is a question mark. mass we have, linear acceleration is a question mark. So at first glance, it looks like we have force tension is the same. So one unknown, two unknowns, alpha, three unknowns, right? And what I said is when you have two equations, you can have two unknowns. So at first glance, it looks like we have one too many unknowns. But what I'm about to show you is that we actually are A-okay. Because what we can do is we can substitute, we can use a bridge equation on that alpha. And so what we can do is we can go force tension, keep this in the same color, we can go force tension times radius equals 1/2 mr squared times linear acceleration over radius, right? Because that's what alpha is. Alpha with the bridge equation, if we divide it by radius, then we can substitute linear acceleration over radius in for alpha. So now we see we only have two unknowns, force tension and linear acceleration. So now two equations, two unknowns, we can now do a substitution. So what is even cooler is that this equation, this net torque equation, simplifies a lot. Because here we've got 1/2 mr squared, right? And that means like r times r squared. So we can take this radius in the denominator and cancel out one of those two r's. And then we can take this radius over here, divide it over and cancel out the other r. So this equation simplifies a lot to just force tension equals 1/2 ma. Okay. Any questions? Let me pause. Scooch this down a little bit so it doesn't get too jumbled. And now we're going to do our substitution. So what we're going to do is we're going to take this equation for force tension and substitute it in there. So instead of writing Ft, we're going to write 1/2 ma. So we're going to go plus force gravity, which is mg, minus 1/2 ma equals ma. Okay, any questions now? I'm going as slowly and as carefully as possible, but I want to keep pausing to see if there's questions.
Will this be a video to refer to?
But there's one thing we got to be careful about. These masses, these m's, are not all the same. Because if we take a closer look, we see this mass came from here, and that is the hanging mass. But this mass came from up here, and that is the mass of the pulley. And this mass came from here, which is the hanging mass. So let's put some labels on those m's so we don't get them all mixed up. So this guy is m sub h, this guy is m sub p, and this guy is m sub h, okay? Hanging mass versus pulley, okay? So the last step is we're trying to find acceleration. So we gotta get all the accelerations on the same side of the equal sign. So we're gonna move this over to that side. So here we go, we're gonna go plus hanging mass times g equals hanging mass times a plus 1/2 pulley mass times a. And then we can factor acceleration out. Linear acceleration can get factored out, and we get plus hanging mass times g equals hanging mass plus 1/2 pulley mass times a. We factored the acceleration out. And then finally, we can just divide this over. So we're going to divide that over, and we get our final answer. Hanging mass times g divided by hanging mass plus 1/2 pulley mass equals our acceleration. And you can plug in your numbers and you're done. So it's a lot to take in. And, you know, looking at the work and hearing the conversations you guys were having, a lot of groups were pretty close. You know, I don't know, maybe even some groups were there. But I wanted to make sure that I kind of like talked us through this myself. So let me summarize. So the first thing we did, right, was we drew our free body diagrams, right? We drew our free body diagrams. We had to think about which way was positive, which way was negative. For our rotating pulley, we wrote out net torque equals I alpha. For our hanging mass, we wrote out net force equals ma. And then we kind of manipulated the net torque equation until we got to something that we could plug in to the net force equation. And then we just kind of, we move the accelerations to the same side. And then we just algebraically simplified until we got our equation for acceleration.